All right, guys, today we're going to be talking about textbook section 2.1, describing location in a distribution. So let's see what it says. It says the pth percentile of a distribution is the value with p% of the observations less than it. So in this first example, it says here are the scores of all 25 students in Mrs. Pryor's statistics class on their first test. So we have 25 data values. Okay. What I did before I started the video is I actually put this data into list 1. Now remember, our calculator can sort these for us. So I put all the data in. Now I'm going to sort the list. So I'm going to go stat, sort ascending, calculator, take all the data in list 1 and sort it ascending. And it'll say done. Now I'm going to go back under my lists. And now it's going to put them in order from least to greatest. So what I'm going to do here off to the side is I'm going to write these data in order. So 67, 72, 73, 73, 74, 75, 77, 77, 77, 78, 79, 80, 80, 81, 82, 83, 83, another 83, 84, 85, 86, 89, 90, and 93. So that's what the data is in order from least to greatest. So it says use the scores, all right, use the scores to find the percentiles for the following students. So Jenny earned an 86. Okay, so if I were to label these data points, this would be data point 1 and this would be data point 25. So Jenny, who got the 86, if this is the 25th data value in order, that would be the 24th, 23rd, 22nd. So this is the 22nd data value. So to find the percentile for Jenny, how many people are below that? Well, 21 people scored less than she did. So all we do is we take 21 over 25. Okay. So if I do divide 21 by 25, it's 0.84. So that means Jenny is in the 84th percentile. Okay, because 84% of the people scored at that or below it. Now, what about for Norman here? Norman earned a 72, so here was his score. This is the second data value. Okay. There's only one person that scored lower than he did. So we do 1 over 25, and that equals 0.04, so Norman is in the 4th percentile. Only 4% of people scored below him. Now, what about Katie? Katie earned the 93. She actually did the best, but this is not the 100th percentile. You can actually never get to the 100th percentile. 24 people, this is a 25th data value in order. 24 people scored below her. Okay, so that would be 24 over 25, and that's 96%. So Katie is in the 96th percentile. And the two students, there's actually two students who scored an 80. So here was the first one. Okay, here was the first one. Remember, it's how many people scored less than an 80. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 people that scored less. Okay, so you would do 11 over 25 based on the definition that we're using about percentiles. Okay, so if you do 11 over 25, that's 44%. So that's the 44th percentile. Now there are other definitions of percentiles. Some people would do 12 because there's 12 people. Some people would use 12, some people would use 13, but based on this definition we're using, we're just considering percentiles, how many people scored less than that score. Okay, so the two students who earned an 80 are both in the 44th percentile. Okay. Now we're going to talk about cumulative relative frequency graphs. So we know one type of frequency graph is a histogram, okay? So we're used to histograms to display frequencies or relative frequencies. Now when we add this word cumulative in front of it, that means to add up, okay? So to create, and the name of this cumulative relative frequency graph is called an ogive. Okay, that's the fancy name for it. So to create one of these things that we're going to study, you take the cumulative frequency, divide by the total. Use the resulting decimal or corresponding percent. Okay, so that's the type of graph we're going to make. So let's look at an example. It says the frequency table below summarizes the ages of the first 44 U.S. presidents. So that goes through President Obama when they were inaugurated. Part A, expand the table to show the relative frequency, cumulative frequency, and the cumulative relative frequency. So we already know that these are the frequencies. If we added up all these frequencies, we have 44 presidents. Okay, so that should add up to 44. Let's just do a quick check. 2 plus 7 is 9, plus 13 is 22, plus 12 is 34, plus 7 is 41, plus 3 is 44. So what would the relative frequency, how would we figure that out? We would take 2 over 44. So I'm just going to put these into the calculator. 2 over 44 is about 4.5%. So I'm just going to round to the nearest hundredth. Okay, I'm going to round to the nearest hundredth. So there 5% of the presidents were between ages 40 and 44 when they were inaugurated. 7 out of 44 presidents were between 45 and 49. So if I do 7 divided by 44 and round it to the nearest hundredth, that would be 0.16 or 16%. Okay, 13 out of 44. If I round it, is 0.30%. 12 out of 44. Rounded to the nearest hundredth is 27%. All right, 7 out of 44, we actually already have that up there, so I know that's going to be 16%. And 3 out of 44, rounded to the nearest hundredth, is 0.07%. Now, if I add up these numbers, 5, 16, 30, 27, 16, and 7, it should be really close to 100%, but it could be slightly off because I rounded, okay? So for this one, it actually adds up to 1.01 or 101% because of rounding error. That's okay. All right. Now, when we talk about cumulative frequency, we actually add the frequencies together. Okay, so let me show you how that works. So for the first one, it's going to be the same thing. It's going to be 2 out of 44, which again is 0.05. Well, that's the cumulative frequency is just, sorry, I did this the wrong way. That's just 2, because there's 2 people, because these are just raw frequencies. Okay, but a cumulative frequency says, okay, how many people were 49 or younger? So you have to add these 2 numbers together. So 7 plus 2 is 9. Then you need to take this 9 and add this 13. So that gets me up to 22. Plus this 12 gets me up to 34. plus this 7 gets me up to 41, plus this 3 gets me up to 44. When you get to the last row, this number should equal the total. Okay. Now to find the cumulative relative frequency, this is relative, so we're looking for percents, just like we were looking for percents there. Okay, so here we do 2 out of 44, which happens to be 0.05. Now I have to find 9 out of 44. Okay. 9 out of 44 is rounded to the nearest hundredth, again, would be 0.20. 22 out of 44, you can probably do that in your head, that's a half, so it's going to be exactly equal to 0.50. Okay. If you do 34 out of 44, let's put that in, that's 0.77. All right, if you do 41 out of 44, it's 0.93. Now obviously 44 out of 44 would be exactly equal to 1. Okay, and you can express these as percents. So you could express this as 5%, 20%, 50%, so on and so forth. All right. So what do these numbers represent? 5% of the presidents were age 44 or younger. 20% of all U.S. presidents were 49 or younger. 50% of the presidents, 54 and younger. 77%, 59 or younger. 93% were 64 or younger. 100% were 69 or younger. All right, so part B here says plot a cumulative relative frequency graph. And this is a fancy name for, or the fancy name for it is an ogive. In the space below. There's not enough space below, so I started it on a separate sheet of paper. So here we go. I'm just going to put this off to the side. So here's how we're going to make this ogive. Okay. We're going to put the cumulative relative frequency, so we're going to start from 0% all the way up to 100%, or as a decimal from 0 all the way up to 1. And on this axis, we're going to put the last age that fits into that bin. Okay, so I'm actually, since the table starts with 40, there's no presidents that started at 39. Okay, there's no president that was inaugurated when he was 39. And that's not me being sexist, because all the presidents so far have been men. Okay, so nobody was 39. Now, how many were 44 or younger? We have it right here. It's 5%, okay, or 0.05. So above the 44, I'm going to go to 0.05. Now, the way I scaled, every tick mark is 0.05. Okay. Then 20% were 49 or younger. So at the 49, I'm going to take it up till it hits roughly about 20%. So maybe about right there. Looks about right. 50% were 54 or younger. 77% were 59 or younger. So take this up to the 59 up to 75%, and it's in between, somewhere in between 75 and 80, which might be about right there. Right. For 64, 93% of presidents were 64 or younger. So take that up till you get to 93%. And I know I didn't scale that very well, but that would fall about right there. Okay, and 100% of presidents were 69 or younger. Okay, so that's where we put the points, and what we do, I'm not going to do this very well, but we're just going to connect each point with line segments. So that's kind of what this ogive would look for. You can give it a title. You can say ogive for presidential or U.S. presidential inauguration age. Okay. All right, so that's how you do an ogive, or a cumulative relative frequency graph. And this is powerful. I'm going to give you a little bit more information about this graph. For instance, if they ask you, what is Q1? Okay, what's the first quartile? Let's say that was a question and they gave you this graph. Well, we know the first quartile is the 25th percentile. So to find where Q1 is, take the 25th, this cumulative relative frequencies, these are the same things as percentiles. Okay, that's what they are. Cumulative relative frequencies are percentiles. Okay, so take this 25 over, estimate where it hits the graph, and then take it down. Okay, so the 25th percentile would be, just estimating, that would be around 50 years old. Okay. Okay, so the Q1 here would equal 50. Okay. What about the median? Well, the median is the 50th percentile. It means half the presidents are older than this age. That falls at an exact point. So when I take that down, the median age for a president is 54 when they're inaugurated. All right, for the 75th percentile, take that across. That's slightly before the point, so bring that down. Okay, so maybe about 58. So you can use an ogive to find Q1, the median, and Q3. And how would you find the IQR? Well, you would just do 58 minus 50. So the IQR there would be 8. All right. So let's answer a couple more questions on this first page. The first one says, was Barack Obama, who was inaugurated at age 47, unusually young? Okay. Well, Barack Obama fits into this category, or into this bin. Okay, so 2 presidents, at least 2, were younger than he was when they were inaugurated. Okay, so if you want to think about percentages, let's go back to our ogive. Okay, let's go back to our ogive. He was 47. Where would 47 fit into this graph? Well, if this is 44 and this is 49, 47 would fit right in between there. If we take that up to the graph where it hits the ogive and take it across, okay, to me, like it looks like it hits maybe around somewhere between, this is 0.10, that's 0.15. So maybe about 12%. 12% is an estimate. So we would say here that Barack Obama is in the 12th percentile. To me, that's not quite low enough to be unusual. If it was less than like 5, if he was lower than the 5th percentile, I would say that that would be unusual, okay? But that means that roughly about 12% of the presidents, based on our graph, our ogive, were younger than he was, okay? It's in the 12th percentile, so I would not consider his inauguration age to be unusually young. Now the last question on this exercise. Estimate and interpret the 65th percentile. So let's go back to our ogive. We can take the 65th percentile, that's 75, that's 70, that's 65th. Okay, take that across until it hits the ogive. Okay, and then take it down and let's just estimate. Okay, to me that looks right, pretty close in the middle between 54 and 59. Okay, so maybe about 57. That would be my estimate. So the 65th percentile is an inauguration age of 57 years old. Okay, what does that mean? That means that 65% of the presidents were 57 or younger when they were inaugurated. So that's going to do it for that question. All right, now we're going to move into talking about z-scores. Okay, so a z-score is a standardized value, a way to compare two people that are in maybe different classes or different distributions. All right. So here's how we're going to find it. To find a z-score, you take the person's actual score minus the mean of that distribution and divide it by the standard deviation. Okay, or another way to think about that is observed minus expected over the spread. And the z-score tells us how many standard deviations from the mean an observation falls. So the bigger the number, okay, the farther it is away from the center. Okay, so the larger the value, the more, or I should say the further that value is away from the mean. So think about like salaries. If the average salary in America was $50,000 a year and LeBron James made $20 million a year, maybe the standard deviation was $10,000, he would be very, very far above. He would have a very, very large z-score. Okay. So if a person has a positive z-score, their value is larger than the mean, because if x is bigger than the mean, the numerator becomes positive. And we know standard deviation is always positive. All right, so if the x is bigger than the mean, z is going to be positive. If the x is less than the mean, then it's going to be negative. And if they're exactly equal to each other, then the person or that observation is at the mean. It's equal to the mean. All right, so let's go to the first example here. It says, use the information from Mrs. Pryor's class to find and interpret in context the standardized scores for each of the following students. If the class mean was 80, okay, and the standard deviation was 6.07, okay? So here's the formula, okay? Z equals the score, which we'll just call the x value, minus the mean. We use mu if it's a population mean, over the standard deviation. Okay. All right, that's the symbol for mean, that's the symbol for standard deviation. So Katie scored a 93. She had the highest score in the class, if you remember. So 93 minus, they tell me here that the mean was 80. Let's confirm that real quick. Remember, my data was in list 1, so if I go stat, calculate one variable stats. Okay, there it is. There's the mean. Mean's 80. Okay. All right. So 93 minus 80 over, actually I'm going to get rid of this. We shouldn't be using 6.069 because that's for a sample. We have all the data in the population. So we really should use let's call it 5.95. Okay, so just change that on your note card, 5.95. So we put 5.95 down here in the bottom. All right, so let's do this calculation for Katie. 93 minus 80, and that's 13. I'm going to take 13 and divide it by 5.95. So that's 2.18. So this is Katie's z-score. So Katie's score falls 2.18 standard deviations above the mean. Okay. So what can we say about Katie? She's smarter than average. Okay. Now let's talk about Norman here. We want to find out his z-score. X minus mu over sigma. Okay. So he's earned a 72. So we do 72 minus 80 over 5.95. Right. So 72 minus 80 is negative 8, 5.95. If I put that in my calculator, it's about negative 1.34. So Norman's score falls 1.34 standard deviations below the mean. Okay, because he has a negative z-score. All right, so let's look at number 2. It says, after receiving an 86 from Mrs. Pryor, Jenny earned an 82 on Mr. Goldstone's chemistry test. At first, she was disappointed. Then Mr. Goldstone told the class that the distribution of scores was fairly symmetric, with a mean of 76 and a standard deviation of 4. It says, on which test did Jenny perform better relative to the class? So the problem with just looking at scores, okay, so here was the information, here's her score on Mrs. Pryor's class. So let's figure out about Jenny. Okay, so she scored 86 on Mrs. Pryor's stats test. So let's figure out how she did in terms of her z-score. So z equals 86 minus 80 over 5.95. So if I simplify that, that's 6 over 5.95, and I know that's going to be slightly more than 1. So that's going to be 1.01. So what does that mean about Jenny? Jenny scored 1.01 standard deviations above the mean for stats. Okay. Now, let's think about, even though this says she got an 82, which seems like it is a lower score, there's no doubt about that, but did she actually do better on it in comparison to her classmates? She might have. The only way we can compare two things is to look at them relative to the other students. It's just like your math scores might be lower than your English scores, but you might have done better overall on math relative to the people that were in your class. Okay, so she got 82 on chem, okay, on Mr. Goldstone's chemistry test. So let's figure out what her z-score was on that. Well, she got an 82, but what was the mean there? Okay, the mean there was 76, so it had a lower mean. It also had less spread. The spread there was only 4. Okay, so here, 82 minus 76 is 6 over 4, and as a decimal, that's 1.50. So relative to her peers, she actually did better on chemistry, because on chemistry, she's 1.5 standard deviations above the mean. On statistics, she's only slightly over 1 standard deviation above the mean. So she actually did better relative to her peers in chemistry. Okay, so that would be your justification. Relative to her peers, Jenny scored better on her chemistry test with a z-score of 1.50, which was higher than her z-score of 1.01 on her statistics test. So this is a way to compare two distributions, is to be able to use z-scores. The next part of this section, we're going to be talking about transforming data. Give me 1 second here, y'all. So it says below are the test scores from an AP Stats first class test. And this is different than the initial information. It says plot the test scores on a dot plot and cuss it. Okay, so just a little review here. So let's go ahead and put the data. Okay. I'm going to put the data into list 1 here. So 71, 92, 65, 88, 78, 73, 89, 83, 90, 67, 79, 54, 97, 61, 84, 77, 59, 71, 81, 62, 76, 85, 93, and someone who got a 48. Okay, so if I go back to the last one, there's 24 data points. Let's make sure we got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I see there's 2 rows. So 12 plus 12 is 24. And just like before, I can sort the data. So stat, sort, ascending, list 1. And go back into it and look at it. All right. Now I notice when I sort the data, I have a 9. Okay, I have a 9. So I missed something. There's no score up here that's a 9. All right, there's no score that's a 9. So when you make a mistake, it's one way to kind of check yourself that maybe you made a mistake. Okay, so I don't know where I made the mistake. So I'm just going to re-enter the data. I didn't mean to make a mistake. Mistakes happen sometimes. 83, 90, 67, 79, 54. I'm just going to take a little bit more time to plug them in this time. 97, 61, 84, 77, 59, 71, 81, 62, 76, 85, 93, 48. I'm going to resort the list. Stat edit. Okay, so 48 is the low one. I know that should be the low one. All right. So let's go ahead and plot these. Okay, let's plot these on the dot plot. So hopefully you remember how to do that. All right. Okay, 48 is the lowest one. All right, so 48. Okay, maybe I can scale by, I don't know, 5s. 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63. And I know the biggest one I think is 97 there, so I have to go up to 97. 64, 65, 66, 67, 68. 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98. So I just scaled by 5 and I started at 48. Okay. So this is scores on AP Stats, student scores on AP Stats first test. Okay, so it asks us to make a dot plot. All right, so just going down my list here, somebody had 48, then someone had 54, then 59, then 61, then 62, then 65, then 67. Okay, 2 people had 71, 68, 69, 70, 71, 73, 74, 75, 76, 77, 78, 77, 78, 79, 81, 83, 84, 85, 88, 89, 90, 92, 93, 97. Okay, so there's my dot plot. All right, and for purposes of time, okay, I'm not going to cuss this, but I could look at this and try to find where's the center. Okay, I could talk about the center. I could talk about unusual features. The data here looks pretty close to each other. This value might be an outlier, so I could calculate if it was or not. Okay, but after I found my 5-number summary, I could make a box plot. Okay, the shape. Okay, shape, I don't see any. Okay, it doesn't, it looks fairly symmetric. Okay, from the center, it goes roughly about that many out that way, about that many out that way. Okay, it might be slightly skewed, or you know, you could figure out what the mean and median was. If the mean is smaller than the median, it's skewed left. This might be slightly skewed left. And then you could talk about spread. You could talk about IQR, or you could talk about standard deviation. Okay. So it says the teacher decides to scale the test by 10 points. That means she's going to add 10 points to everybody. Okay. So if that happens, think about all of these numbers changing by 10 points. So if that happens, the person that got 48 now would have a 58. And the person that got a 97 would now have 107. Okay, but what do you notice there? Okay, what effect did the 10 points have on the graph? All it did is it changed a 48 to a 58, and it changed this 97 to a 107. Okay, so what effect? It just shifted the graph 10 units to the right. But the shape of this distribution is preserved. Okay. So what would happen here? The center would go up by 10. Okay, the center would go up by 10, but the spread would not change. Okay, it would not change. The shape would not change. Because you're just shifting it. Everything else is preserved. The amount of spread, like even the range here, if I took 97 minus 48, that's a range of 49. If I add 10 to everybody, 58, 107 minus 58 is still the same number. That's still 49, so it does not change the spread. Okay. So what can we conclude about the effect of adding or subtracting a constant? Okay, the mean, or I should say the center, okay, goes up or down by a constant. Okay, that's the only thing that changes. Shape is preserved. Okay, spread is preserved. So no matter which measure of spread you use, if you use standard deviation, that number would stay the same. If you look at IQR, that would stay the same. If you look at range, that would stay the same. Okay. So those things are preserved. And then if this was an outlier in the first distribution, even if you add 10 points to it, that would 58 would also be an outlier in the second distribution. All right. So after much thought, the teacher decided to instead scale their test by a factor. So that means she's going to multiply all the scores. Okay, so you're going to multiply all the scores. All right. So let me just, before I do that, let's get some descriptive statistics. Okay. So let's go stat, edit. Oops. Go stat, calculate one variable stats for list 1. Okay, so let's just write some of this down. For the original, okay, the mean was 75.95 or 96. Okay, that's a measure of center. We can write the median as well. The median is 77.5. Okay, and let's do the spread. Let's find the population standard deviation. Sigma here is 12.86. So that was the first distribution. Okay. All right. Now for the second distribution, there's an easy way to do that. For list 2, if I want to add 10 points to everybody's score, just say, okay, calculator, up at the top where it says L2, say take L1 and add 10 points. Okay, so now it adds 10 points to all of those things I had in list 1. Now let's run statistics on that. So let's go stat, calculate one variable stats for list 2. Okay, let's look at that. Okay, so look over here. The X bar when I added 10 points, so this was adding 10 points. And the X bar here is 85.96. The sigma is 12.86. The median, if I scroll down, is 87.5. So notice what happened to the center. Here was the original center, whether that's the mean, that's the median. But when I add 10 points, what did that do to the center? It added 10 points, exactly 10 points to both of those. But what stayed the same? The amount of spread or standard deviation stayed the same. Now for this next one, we're going to do something different. We're going to multiply each score by 1.2. So what would happen to this lowest score, 48? If I took 48 times 1.2, that person would now get a 57.6. Okay? So if you think about how much the person's grade changed, that person got, that was the effect of basically getting 9.6 more points. But what about the person that got 97? If you take 97 times 1.2, so this person actually now has a 116.4. So this person basically got an extra 19.4 points. Okay, so the better they did, the more of a bump they got. These are not the same number. Okay, they're multiplying by the same number, but the effect is different. Higher scores get more of a bump. So if I did that for all the points on this dot plot, the original spread was 49 units long. What would the new spread be? Well, we start there. Okay, so here's what I'm talking about. If I want to find the range of this distribution, okay, there's 49 points difference between the best and the worst. Okay, but what would the new spread be here? Well, what's 116.4 minus 57.6? Okay, the range now becomes a 58.8. And hopefully you recognize that 58.8 is 49. It's the original spread, one measure of spread, which is range. times 1.2 as well. Okay. So when you multiply each score by 1.2, it changes the spread. It's going to change the spread as well. Okay. So let's look at let me rewrite the original data again. Here's the original. The original mean was 75.96. The original median was 77.5. And the original standard deviation was 12.86. Now, what about when we take the original and multiply the data by 1.2? So let's go under here, let's go under our list. So we'll go stat edit. Okay. Now I'm going to put that into list 3. So I'm going to say take my original data that's in list 1 and multiply it times 1.2. So this 48 becomes a 57.6. The 54 becomes a 64.8. All the way through until the best score is now a 116.4. Now if I run my stats again for list 3, okay, I'm going to write this data down. The new mean, okay, after I multiply all the numbers by 1.2, the new mean is 91.15. The new median is 93. Okay, the new spread is 15.43. Okay. So when we added a number, it changed the center, but it didn't change the spread. When we multiply by a number, it changes the center. Okay. If you took 75.96 times 1.2, you would get 91.15. Okay. 77.5 times 1.2 is 93. But unlike when just adding a number, look at the standard deviations. Now the standard deviations are different. Okay. Now the standard deviations are different. The spread is bigger. Okay. The spread is bigger. So to get from here to here, you have to multiply by 1.2. Up here, you didn't do that. When you just add a number, there's no change to the spread. All right, so you can talk about that. Center goes up by the factor. Okay, and that's times. All right, and spread goes up by the factor. By that 1.2. Okay. The shape, okay, shape is preserved though. Okay, if we actually looked at the data in list 3 and plotted them out like we did with the original data, shape is fairly preserved, but it's going to get wider. Okay, the graph's going to get wider because there's a bigger range. Now the range is 58.8, but the general shape will be preserved. It'll still look like this, but the points are going to be separated by a little bit more. Okay. The points will be separated a little bit more. Okay. So the effect of multiplying or dividing by a constant, it means it changes center and spread. Now, how are these transformations connected to z-scores? It says now that we know how a set of data is affected by adding or subtracting a constant and multiplying or dividing by a constant, notice that when finding a z-score, I subtract and then divide. Okay, so basically, let's look at this first person. Okay, in the original, take the person that got a 48. Okay, the mean here was 75.96, and the spread was 12.86. So let's figure out what the z-score for that person that did the worst. 48 minus 75.96. That's negative 27.96 divided by 12.86. And that's negative 2.17. What about when we looked at this? What about the person that, what was the person's score if you multiplied 48 by 1.2? Well, their score turned into a 57.6. Okay, and the spread of that distribution was 15.43. Well, if you think about this, if you actually do the math, all right, that's negative 33.9 divided by 15.43. Okay. And that's going to be basically the same. Okay. It's going to be roughly about the same. All right, if I actually used all the decimals, they would be exactly the same. Why is that? So basically, do z-scores change even when you multiply or add by a number? Well, when you multiply, definitely not. Okay, when you multiply, definitely not. All right, so why is that? Because here, if I factored out a 1.2, this would become the original data. It'd be 48 minus 75.96. If I factored out a 1.2 here, this would be 12.86. Okay, so the 1.2's cancel, and you get back to the original thing. So when you multiply by a number, okay, it does not change the z-score. And what about when you add by a number? What about when you add by a number? That 48 became a 58, the mean became an 85.96, but the standard deviation stayed the same. Okay, so here both of these are 10 higher, so if you subtract those, it's still negative 27.96, and this is still 12.86. So it matches that exactly. So no matter how you transform data, the z-scores are always going to be the same. Okay? The z-scores will always be the same. All right, so they're still in the same relative position or same relative standing to their peers, no matter what you do to a data set. So that's the important thing. Z-scores always stay the same, so that's the big takeaway. Z-scores stay the same regardless of transforming data. Okay. All right, so last topic in this first section is about density curves. So it says, after we have plotted our data, found an overall pattern, and calculated a numerical summary to describe the center being mean or median, and spread, usually being standard deviation or IQR, we find one more step to exploring our quantitative data. Sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. So a couple things about density curves there. Okay, it's always on or above the horizontal axis. These are 3 examples of density curves, by the way. All right. Has an area of exactly 1 underneath it. So if I were to be able to use calculus and calculate the area of these curves, the area always equals 1, or always equals 100% of the people. All right. Describes the overall pattern. So like this curve right here, this density curve would be considered skewed left. This one would be considered skewed right. And this one is approximately symmetric. All right. Outliers are not described by the curve, and the curve is an approximation. All right. So thinking about density curves, the median of a density curve is the equal areas point. Half the area is on the left, and half of the area is on the right. And the mean of a density curve is the point at which the curve would balance if made of solid material. It's basically like a fulcrum. Okay, it's basically like a fulcrum. It tells us here that the median and mean are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is always pulled away from the median in the direction of the long tail. And the mode is the tallest value on the graph. So our example here is in each of the following density curves, determine which line represents the mean, which line represents the median, and which line represents the mode. All right. Justify your answer and note that some lines may not represent any of these three measures. Okay. So let's start with the mode. So the mode is the high point in the graph. So in this first graph, that's definitely the mode. Okay. In the second graph, that point is the highest, so it's also the mode. Okay. And in the third graph, this is the high point in the graph, so point A is the mode, because it's the high point. All right, now what about median? Median is the equal areas point. All right, so if I think about in the second curve, B is actually the median. Because if I think about the area to the left of that, okay, if I were able to calculate the area there, it would be exactly the same as the area over here. Okay, that's the equal areas point. All right, and here in the second curve, A is actually also the median because those have equal areas to the left and to the right of it. So the median in the second curve is at A as well. Okay. And then the third graph here, at point B, this is the median. Because there will be equal area to the left and to the right. Now, how do I just know these things right off the bat? Okay. What about the mean? The mean is like a fulcrum. If this shape was made of solid materials, where could I put my line so it would balance? And that happens here at A. Okay. In a skewed distribution, since this is skewed, there's a few low scores. That makes me think it pulls the average down. Okay. A couple bad scores on a test pulls your average down. So if it's skewed left, the mean is always less than the median. If the distribution is skewed right, like this one, there's a couple people that make high salaries, that pulls the average salary up. Okay, so here, that's where the mean is. And if the curve is completely symmetric, then the median is also the location of the mean. So the mean is at A as well. Okay, so if the curve is symmetric, the mean and the median fall in the same place. But if the curve is skewed, like these two, the mean is further in the direction of the long tail. So the mean is greater than the median here, and this one, the mean is less than the median because it's skewed to the left. So I think that's going to do it. That's the end of section 2.1. Hopefully the explanations helped you, and just let me know if you have any questions and do that in class.